Hi class, we are moving on to section 9.3. We're going to discuss the matrix of a linear transformation. Basically, we're going to talk about how to find the matrix for a linear transformation. More so, we're going to be talking about column vector representations in different bases. I suggest that you revisit section 4.4 and just kind of review that section, that video, or that write-up if you're in my class. I'm going to make the same suggestion for chapter 9.4. You can probably get through this section without the review, but for the next section, 9.4, I highly suggest that you review the 4.4 video. It'll definitely help you for this video as well. There's kind of a lot to unpack here and in the next video as well. So you may need to view this video a couple times before everything makes sense. Okay, so let's go ahead and get started. We'll start with the definition. Okay, let V be a vector space that has a basis G. So G has, in this case, M vectors. For every V that we have inside of a vector space, we can represent V in terms of the basis vectors in this form. So again, this is not new. We have done this several times before. It's always good to review this though, because it's not that natural for us, right? So V has a unique representation under these basis vectors by using this unique linear combination, right? C1, C2, all the way up to Cm, where the Cm's, each Ci is a scalar value, right? So we define what's called the coordinate vector of V with respect to basis G by the representation of V by the scalar values that we need when we write this linear combination. Okay, so it's very important that you recognize what this is. Every time you see the little bracket with the subscript of the basis, you will have a column vector. Okay, it will always be a column vector no matter what space we're in. This is the coordinate vector representation of this vector according to this basis. So regardless of if these are functions here for the basis vectors, if they're matrices, your representation under that basis will always be basically the scalar values that represent the linear combination of these basis vectors for that vector representation in that basis. Okay, it's very, very important that you understand that, because we're going to use this all over the place and it can get very, very confusing. I know I had to review several times before making this video and write my lecture notes, but maybe that's just me, right? So in general, okay, although this is expressed in terms of a vector in Euclidean M space in this case, it's still a vector in V. So as I said, if our vector space represents functions, even though our representation as a coordinate vector is a standard Euclidean vector, it still represents whatever type of vector object we have in our vector space. So this still can represent a function, a polynomial, a matrix, right? But its coordinate vector representation is always going to be one of our standard Euclidean vectors. Okay. The choice of basis matters, meaning if this is my basis, right, this will be my representation. If I have a different basis for the same vector space, my vector representation will change, and this coordinate vector representation will change as well, because I'll have different scalar values to represent the same vector, because I'll have a different set of basis vectors, right? It'll be a different linear combination. Okay. So different bases will give different coordinate vectors for the same vector V, right? The order of bases matters. If I were to swap G1 and G2, I would also have to swap C1 and C2, and then my coordinate vector representation with respect to G would change. It would be C2, C1, and then so forth, right? So the order that I have my basis vectors is going to affect the order of my representation under that basis, which is going to affect what my coordinate vector looks like. Okay, so the order of the vectors in our basis matters. right? So again, just like we've been doing, we read them from left to right, and when we take them for computations, we take them in that order from left to right, okay? Since G is a basis for this vector space, okay, the scalars here are unique, as I said a couple of minutes ago, right? So for each v, right, so for every vector in this vector space, there is exactly one coordinate vector with respect to this basis. So as I said earlier, this vector representation is going to be unique for each basis, right? If I change my basis, I'll have a different unique representation, meaning these C1, C2s, CMs will change if I have a different basis, right? So let's jump into an example. These first two examples will be really easy, but you should really remember them, because we are going to be using these notations and these standards for all of the problems in the next two sections. So they seem very basic right now, but they're very important. So just hold on to what it is that we're doing for the next two examples, and just keep that in the back of your mind. If you're writing your lecture notes, as you should be when you watch this video, put huge stars next to them, okay? Okay, so we want to find the coordinate vector of v equals negative 11x with respect to the basis g, which is given by negative 3x plus 2 and 2x minus 5. Okay, so we want to find the coordinate vector representation according to this basis. So remember what that means is that I basically need to write v as a linear combination of these two vectors, right? That's where we're coming from here, right? So I want to write v as a linear combination of the given basis vectors. That's it. I'm not so I'm trying to find the coordinate vector, so I want to find this. So I really just need the C1 and C2 for my example, so that I can write my v under the representation given. So I'll have a 2, since I have two basis vectors, I can write v as a 2-element vector, right? Standard R2 vector. Okay, so I need to write negative 11x as a linear combination of these two, which is easy. We've done that quite a bit. So this is what I need. I need to find C1 and C2 so that when I add them together, I get negative 11x, right? So I set up my equation. Negative 11x equals some constant multiple of my first basis vector plus some other scalar multiple of my second basis vector, and I just solve, right? So we can solve this in several ways. Again, stay away from standard algebra. At this point, everything should be in terms of matrices and linear algebra. I don't want you guys solving the stuff, you know, like you would if this was an Algebra 2 course at this point. So notice that we can turn these into column vectors, right? Is one way to think about it, how we the standard practice. So I know that negative 3x plus 2 C2x will equal negative 11x, and that 2c1 minus 5c2 will equal 0 constants, right? So I can turn this into two different equations, right? Notice again that these are basically column vectors at this point, right? So we should be used to doing that. So this is the vector representation, right? You can do RREF, but if I'm setting up in this way, it's very obvious that I'm looking to use an inverse here. Inverses are generally easier to do, especially if it's a 2x2 matrix. Whatever you guys want to do to solve. I know we're using calculators at this point, but let's try to stay with inverse matrices whenever we have a square set, which we should have when we're using bases, right? Bases for a vector space at least. So I'm just going to multiply on the left both of these by the inverse matrix of this. Okay, so C1 will be the inverse matrix of this times my resultant vector, which will give me 5, 2. So that means C1 is 5, C2 is 2. I have my vector right away, right? So my coordinate vector representation under this basis G is 5, 2, right? So the representation of V and G is 5, 2. That's it, right? So again, these are things that we've done lots and lots of times, but just understand that when I'm representing a vector, even though it's not a standard Euclidean vector, when I'm representing it as a coordinate vector, it will always be a standard Euclidean vector. Okay. So for the next example, we're actually going to just do the opposite. I want to find my vector v, given that I already have its coordinate vector representation in terms of g, where g is the following basis, right? So now I have four 2x2 matrices, and this is its coordinate vector representation. So remember, what is a coordinate vector representation? It means that these are the coefficients for when I write my linear combination of basis vectors. So to go from the coordinate vector representation into the standard vector representation for whatever basis I'm actually working in, all I have to do is write these things out as a linear combination with these as my scalar values. Okay, so again, very, very easy, but we're going to be doing this a lot. This is generally the last part of a much, much larger problem, and it's easy to forget that this is what we want to do. So I'm making a point to mention it a few times so that you don't forget as we go through this video. Okay, so this is what I want. I want the standard representation of my vector v. So I'm going to take it from its coordinate vector representation, and I'm going to write it as its scalar multiple and just simplify it, right? So 1 times the first basis vector, 2 times the second basis vector, C3 times the third, C4 times the fourth, right? And I'll just combine these things together. 1 plus 2 plus 0 plus 2, right? So that's basically just going to give me 5 in the first position, and I'll just go like that through everything. Okay, so I'll just add it up. So my V originally looked like this, and if I want to represent it in terms of a different basis, in this case the basis G, this is its representation in G, its coordinate vector representation in G. Okay. So now let's talk about the matrices of linear transformations. So let's say that V is an n-dimensional vector space, okay, and that W is an m-dimensional vector space, so they have different dimensions. And now we have a linear transformation T that takes elements from V and sends them into W, right? So before, back in chapter 3.1, we would say that T was a transformation from Rn into Rm. However, we're not using standard Euclidean spaces, so this could be polynomials, this could be matrices, right? Again, stressing the fact that we're not always working with Euclidean vectors, right? We have different definitions now of vectors. So let's say that G is a basis for our domain V, okay, and Q is a basis for our domain W, right? So we have two different bases, G and Q in this case. And for every V that we have in our domain space, our vector space V, the coordinate matrices of V and TV respectively are V of G, right? Because the basis for V is G, so anything in V has a representation as a coordinate vector, right, in terms of G. Anything in the codomain in the range, okay, which are images of V under the transformation, will have a vector representation under Q because the basis for W is Q, right? So V goes to T of V, but V has a representation of G in our space V because that is the basis for V. Our outputs, T of V, will have a representation under Q because Q is the basis for our codomain space, our range. Right? So this should make sense, although it's a mouthful to say, right? So we actually have a couple of images that make it a little bit easier to understand what's going on. Okay. T is a transformation that takes X to T of X. But since X is in the space V, and the space V has a basis of G, in this case we'll say B because I didn't have a visual that had G, right? We'll call it B, right? So B is the basis for my domain V, and B prime is the basis for my codomain, my range. So X in my basis looks like X in terms of B. my transformation of x in its space has a representation of t of x in terms of, in this case, b prime. So for our wording here, we're using g and q. Here, b would be my g, b prime would be my q. Okay, so here's a little preview of where we're trying to go with this. So this is basically the step-by-step process of what it is that we need to do for the type of problems that we're doing here. Okay, so how do we find t of v directly, right? So in that case, that's this. Okay, so what we need to do, because we have different bases, is whatever our vector v is, we have to find it in terms of the coordinate vector that it is being represented in, right? So the basis for the space where v lives is g, so we have to find v in terms of that basis. So we find the coordinate vector representation of v in terms of the basis it's in, which is g. Next we do is we multiply v of g on the left by a. A is the transformation matrix of t represented in g. Okay, so it's the transformation matrix of t that maps the vector v of g into t of v in terms of q for every vector v in v. So what it does is it takes this thing and it maps it to this thing. That is what our transformation matrix does. Okay, so once I'm in this space, once I have my transformation in terms of the basis that it's in, I have to reconstruct t of v from its coordinate vector that's in terms of its basis. So basically, I'm doing this example. Okay, so the first thing I do is I do this. I take v, I represent it in the basis it's in. I transform it based on my transformation matrix, and then I take the vector representation and I turn it back into its original form in terms of the new basis that I'm in. Okay, so I reconstruct this part from this part. So I'm basically going from here to here to here to here, right? So you're like, oh, why don't I just go this way? Doesn't A just take my thing and turn it into what I need? Nope, because I have two different basis representations for my space. So I need to take my vector I'm given, write it in terms of the basis that I'm in, transform it because my transformation transforms it into my new space. And my new space has its own basis representation. So I have to reconstruct my vector, my transformation I want from the space that I'm in. So when it transforms it transforms it so that it's already in the basis that I will be going to. So I have to untransform it back into its standard representation. Okay, so this is a much better visual for what's really going on here. This is the part that we really want to look at. So the first thing that I'm going to do is I'm going to take x, I'm going to write it in terms of the basis of the space that I'm in. I'm going to transform it by multiplying it by my transformation matrix. It will give me the transformation in terms of the basis of the space that I'm in. So then I gotta deconstruct it or reconstruct my my vector by multiplying its coordinates, because remember, this is a coordinate vector. These two things are coordinate vectors. So I turn it into a coordinate vector, I multiply it, transform it, it'll turn it into a new coordinate vector, and then I deconstruct the coordinate vector back into the vector that I'm working with. Okay, so that's the step 1, 2, 3. So there is no direct computation. There is a direct computation, and we'll talk about that in the next section, chapter 9.4, but we really have to get a handle on this first before we can proceed to 9.4. Okay, so again, these are the 3 steps of really what we're doing. Now, obviously, nothing in a math book is like, hey, I need you to do 1, 2, 3 all the time. They're going to do things like, hey, here's 1 and here's 3, now figure out what 2 is. Or, hey, here's 3 and here's 2, now figure out what 1. Or something to that effect, right? So we really have to get a handle of what it is that we're doing here so that when they give us certain things or ask us certain questions, we can say, oh, okay, I have this and I have this. This is what they're asking me for. Or I have this and I have this and this is what they're asking me for. So we want to make sure that we're really aware of what's going on in this section. It'd be very confusing because there's lots of notation. So again, the main thing to remember is that when you have these brackets around your vector, or even around the transformed vector, you are using a Euclidean vector at that point. It is a vector, is a coordinate vector representation of whatever function, matrix, or whatever vector space you're in terms of the bases you're working. So I've repeated that several times, so I just want you guys to understand that, okay? So let's move forward. T from V to W is a linear transformation, and G is given by this basis, and it's a basis for our domain V, okay? And Q, again, is the basis for our codomain W. Then we want the following, okay? We want the transformation of our vector V, okay, in terms of Q, in terms of our codomain space, to be given to us by some transformation matrix times the vector that's represented in our vector space, in our domain space, by the basis that forms that vector space. Okay, I hope that makes sense to you. So this is really just a repeat of what we're saying. You take V, you transform it into the basis representation of the vector space you're in. You transform it by multiplying it by your transformation matrix, and your end result will be the image of V, okay, represented in the basis of the space that you are going into. Okay, so again, that's really just a repeat of this. Okay, you take your vector, you write it in terms of your basis, you transform it by A, so that's A times this thing. Okay, take your vector, you represent it in terms of your basis, you transform it by multiplying it by the transformation matrix, and then your output is the image of your vector in terms of the basis of the space that you transformed it into. Okay, and that's what this is saying. This is the mathematical way of representing what is going to be happening in this image, or this step-by-step process. Okay, so we're going to use this equality here to derive some useful things. Okay, so now we're going to be playing around with bases and things like that. So now we're on to the algebra part of this section. So we're going to do some derivations here. Okay, so T of V under the representation of Q is the coordinate vector. So right, it's under brackets, so it's a coordinate vector of the transformation of V. Right, so we transform V, and then we represent it in terms of the basis of the space that we're in, right, which is TV. With respect to Q, A times V in terms of G is the transformation vector of V, right, with respect to G. So we transform V with respect to G, and it turns into a coordinate vector with respect to Q, right? So we're transforming V. V is represented by G. That transformation takes the image of V and represents it in terms of Q. So these two things, these two sentences here are equal, right? They're the same thing. The coordinate vector of the transformation of V with respect to Q is the same as the transformation vector of V with respect to G. They're the same thing, right? So let's break this down a little bit, okay? So let's say this transformation matrix of T that's given by A is a matrix, which it always is, right? And so it can be written as column vectors, where those column vectors are A1, A2, so forth and so forth, up to AM, okay? Our vector V can be represented in this space, right? This vector space V, which has a basis of G, by turning it into a linear combination of the basis vectors, right? So V looks like this. So we saw that from the beginning. So when I multiply A times V in terms of G, I'm really just taking this matrix and I'm multiplying it times, this is a coordinate vector. So V in terms of G is just the C1, C2, whatever, and what have you, right? So this is A, this matrix, times this C1 matrix. So that's what this side looks like. Okay, we're used to that. We've done it several times. So what happens when I multiply a matrix times C1, C2, what have you, I'm really just writing a linear combination of the column vectors that make up this matrix. Okay, so this right-hand side is really just C1 times this column vector plus C2 times this column vector plus so forth and so forth. Okay, so that's a breakdown of the right-hand side. So for the left-hand side, LHS, left-hand side, this transformation of V in terms of Q, okay, well, we know that the transformation of V is just us transforming V, right? So transforming each of these pieces. So we know how linear transformation works. We can transform each of the individual parts. And that's what we're going to do. We're going to transform the first part, transform the second part, and add them all together. We also know that we can pull out constants. So that's the next thing we're going to do. We're going to rewrite this as C1 times T of G1 plus C2 times T of G2 and so forth, right? We know that this is a property of linear transformations. Okay. So if we know that we need to represent T of V in terms of Q, because that's what we're trying to get to, well, in order to write this as a representation of Q, right, the basis vector is Q, I need to represent each of its parts in terms of Q, right? So if I were to represent T of V in Q, each of these parts that we broke apart now have to have a representation of Q. Okay. Now it is not as simple as just saying, okay, so I'm going to write this and multiply it times this basis vector, because this is a vector, right? It's C1 times a vector. I can't just say I have a vector times a vector. Vectors don't work that way, right? Vector multiplication, that would be a dot product in that case, right? So remember, to have a vector representation, I have to have a constant times a vector. So what we're going to do is we're going to represent this vector in terms of this basis. So this turns into a linear combination where we are multiplying it times the basis vectors of Q. And we're going to do this for this one as well. So this turns into a longer combination multiplied by C1. This turns into a longer linear combination multiplied by C2. So it doesn't make sense to write this all out right now because it's not what we need. Really what we need is just that if T of V is C1 times the transformation of G1 plus C2 times the transformation of G2 plus so forth, in order to write this as a representation under Q, I just need to write these individual pieces under their representations of Q, right? So again, since each of these TG sub i's is a vector, their components are dependent on the linear transformation of G. So writing it in terms of Q, I have to rewrite this now as a linear combination in terms of these basis vectors, which again is not necessary. You can try it out yourself if you want to, but it's not necessary for what we need to do right now. Okay, so I need to, as you saw here, I need to equate these two halves because they're the same thing. So what does that mean? It means that AVG, which is this, is going to be the same as this thing. Okay, so that means that C1A1 is the same as C1 times the transformation of G1 represented under Q. C2A2 is going to be the same thing as C2 times T times G times 2 times representation of Q. So if you notice, the C1s, the C2s, all the CMs are the same, but A1 then has to be this vector. A2 then has to be this vector, the transformation of G2 under the representation of Q. A3 would need to be the transformation of G3 under the representation of Q. So the equation portion that we need, the things we need to equate, are the vectors of A, the column vectors of A, with these transformation of basis vectors written under this basis representation. Okay, so again, so equating these two halves, this implies that each A sub I is just the transformation of that vective column vector, respective basis vector written in terms of Q. And that's true for each one, right? So A3 would be the respective, so the third basis vector transformed and then written in terms of Q. Okay. So A is called the transformation matrix of T with respect to G and Q. The order here matters. Okay, I'm going from G to Q. So A is with respect to G and Q, meaning we're going from G into Q. Okay, so let's do an example. Now that we have, we fleshed out this idea quite a bit. So let's say that A is this 4x4 vector. Matrix. So this is our transformation matrix. And that's for this linear transformation that goes from V to W for basis G and Q respectively. So G again is the basis for V, Q is the basis for W, A is the transformation matrix for this that takes a vector in G and transforms it into a vector in the representation of Q. Okay, it's not going from G to Q, it's going from V to W, but from the representation of V into the representation of Q and W. Hope that makes sense. So the vector that we have that's in V under this representation is given to us. So if you notice here, I don't need to know what this basis is or what this basis is if I already have the vector representation in that basis, right? If I know V is already represented in the basis necessary, I don't need to know what this basis actually is. I don't need to know what this basis necessarily is unless I'm trying to find V, which is actually what our question is going to be. I want to find T of V, so notice this is not with the brackets, which is why I would need Q. Okay, so after I transform and do all my stuff, once I get this thing out, I'm going to have to take it from its coordinate vector representation and write it as its vector representation by doing the linear combinations. Okay, so I want to find the transformation of V. So first I have to find the transformation of V under this representation, which means that, so this is what we're using right here, I just need to take A and multiply times V of G, and then my result, we're going to come all the way back here and we're going to do what we did for this last example, right? Where I had a vector in my representation and I wanted its vector not in the representation, so I took its coordinate vector and I multiplied it times the basis, right? So instead of doing this with our initial vector, we're going to do it with our transformed vector. Okay, so I don't want the transformation representation, the image under Q, I want just the image, right? So I'm going to do all of this. I'm going to come out with its image under Q, and then again, this is a coordinate vector representation, so I'm just going to take those, in that case, C1, 2, C3, C1, C2, C3, and C4, and multiply it times these basis vectors so I can get the original out. Okay, so this is what I'm using. This is my golden rule because I'm going from one basis to another. So A is this thing, V of G is this. So I'm just multiplying these two together, right? That's what it's here. So my A times my coordinate vector of V in terms of G, right? Multiply those two, I get something out. So now this is my coordinate vector representation of the image of V in terms of Q. So again, all these are coefficients. These are my scalars. Okay, this is the coordinate vector of the transformation with respect to Q because I transformed my input vector by my transformation. So if I want to find T of V, these are the scalars that I have against the basis here, right? Because obviously the space that I'm going into, W, is 2 by 2 matrices. Okay, I don't know what V is. These could be matrices, these could be polynomials. I don't know. All I know is the coordinate vector representation of something in V. I have no idea what this basis is actually consisting of, if it's functions or what. But since I know what Q is, I do know Q consists of 2 by 2 matrices. So in the end, right? I want a 2 by 2 matrix. So when I do my transformation, I'm getting a Euclidean vector. So I need to take that Euclidean vector and turn it into an object in the space that I'm in, which is 2 by 2 matrices. So I get my coordinate vector, I multiply it times my basis, so I can get an element of what the vectors look like in that space, which is this. So T of V is this. This was T of V with the brackets with the small q on the outside. Okay, so again, it's important to understand what you have and if that's your final answer or not, right? So for us, we don't want the brackets on the outside, so we have to take these scalars and then rewrite our basis vectors as a linear combination for these scalar values to get what we needed to get. Okay, so let's do another example. So we want to find the matrix A, the linear transformation given by t of f of x, so we're plugging in a function, and we are then taking the derivative, multiplying by x, and adding that function evaluated at 0. Okay, with respect to the basis, g is x squared plus 3, x minus 2, x squared plus x for v, and q is x squared minus 2x, x squared plus x plus 4, 3x plus 1 being a basis for w. Okay, so what we want is we want our matrix A, we want the transformation given by this process. We are starting in this basis and we are ending in this basis. So let's again go back through our slides a little bit and figure out how do we find the matrix A. Okay, so remember what I said before. We will be given a few things. Okay, since this is what we're doing, we'll be given 2 of these things and asked for a third, right? Or 2 things and asked for a third. In this case, we're given information about 1 and 3, and we're being asked to find something about 2. I know a basis, but I don't know my transformation matrix. So that's what we're given in this case for this example we're about to work on. So we actually derived how it is that we find these this matrix A through this process in these slides. Okay, I know that A is column vectors, right? I know how to transform and how to find A. It's C1 times each of these A1, A2s, etc. Okay, and then in this process, when we're looking at our left-hand side, we equated it to our right-hand side. And we said that each AI is just a transformation of the basis vector for the basis that I'm in, written in terms of Q, right? So CA1 has to be equal to C1 transformation of G1 in terms of Q, right? So right here was where we found how to find each column vector of our transformation matrix A. So I'm going to take a column, each basis vector, I'm going to transform it, okay, and then I'm going to represent it in terms of Q. That's what I need for this. So we're going to use this relationship to try to find A. Now you might be saying, well, how do I transform it if I don't have the actual transformation matrix? Well, let's go ahead and let's go through this, right? So I'm sure I repeated this information as well because I'm trying to be very thorough here. So each AI is the transformation of G in terms of this. So I have my transformation, I just don't have the matrix for it. So what I'm going to do is going to take this first basis vector, I'm going to transform it as given by my transformation, and then I'm going to make sure it's represented in terms of this basis vector Q. Okay, so again, take G1, G2, G3, transform each one, and then write each of those transformations in terms of the basis for Q, which is the basis for W. Okay, so again, just a summary, transform each basis vector of G and find its representation in Q. Right, so A1 is the transformation of G1 represented in Q. So remember, my transformation is take the derivative, multiply it by x, add it to your basis vector evaluated at 0. Okay. So for the transformation of G1, this turns into 2x because the 3 goes away. I'm going to multiply that by x so that it turns into 2x squared. Evaluate at 0, which is 3. So this should be 2x squared plus 3. Obviously, for this first one, I wrote that whole thing out for you guys. Okay. I'm going to take the derivative, which is 2x. I'm going to multiply it by x. Okay. And then I'm going to add f of 0. This is f of 0. This is the derivative times x. Okay. So I got 2x squared plus 3. So that is the transformation of G1, but this is not its representation in terms of Q. So I need to write this in terms of Q. So I'm going to set up an equation, right? So this needs to be a linear combination. The scalars for that linear combination will create my T of G1 in terms of Q. So remember, this has brackets around it with the basis that I want. So this needs to be a Euclidean vector. It's a coordinate vector representation. This is not a coordinate vector representation. So I'm going to write this in terms of this, and those scalars will form my coordinate vector. So that's what I need to do for all of these, right? So I need 2x squared plus 3 is c1 times this plus c2 times this plus c3 times that. So let's set this up, right? Coordinate vector representation, set this up. So we know the easy way of doing this. This turns into a column vector. This turns into a column vector. This turns into a column vector. But we can write it out the long way, right? I know ax squared plus bx squared plus 0 has to be 2x squared. And I can do that for the x's as well and so forth. But we know how to do this, right? So this is the first column vector. This is the second. This is the third. This is my resultant vector. We did this in an example at the very beginning, the very first example we did, right? So if you're like, where the hell does this come from? Go look at the very first example. We're really doing the exact same thing, right? So what we're going to do is we're going to take this, and in order to solve it, I have to multiply this resultant vector times the inverse that I'm doing, right? So just so that we're clear, just because remember, I said the very first two examples were the most important. They're the things we're going to be doing all the time, right? I needed this in terms of that, so I wrote it as two equations. I turned it into a matrix times my scalars equals my result. So in order to find this, I had to multiply times the inverse on the left hand side, right? So that's exactly what we're doing, this thing, but for just a different problem right now. Okay. Okay. So I'm just skipping some steps, right? So from here to here, I skip some steps because I'm assuming you guys know what we're doing. So just to go back, that's where this comes from. So this then is that vector representation. That's the C1, C2, C3, or the A, B, and C scalars that I need in order to represent this vector in terms of Q. Okay, so that is my vector representation. So that would actually be the first column vector for A. Okay, and then we're going to do the same thing for the next two. So A2 is a transformation of the second basis vector of G, written as a coordinate vector in terms of Q, right? In representation of Q. So I transform the first column vector, the second one, which is x minus 2. Under that transformation, I get x squared minus 2. So remember, I'm taking this derivative, I'm multiplying it times x, and then I'm adding to the end of that this evaluated at 0, right? So that's where we get this from. To find this, I do the same thing. It's going to have this exact same representation on this side, but instead of being equal to 203, it'll be equal to 1, 0, negative 2. Right. So when I multiply this out, we will get this result. Okay, and that will be my A2 vector. So I just do that again with the third vector, right? For the basis of G, x squared plus x. Do the same thing, take the derivative, multiply it by 1, evaluate at f of 0, then write it in terms of this representation, right? So everything is, a lot of it is the same. So, okay, transform G3. Transformation of G3 is the transformation of x squared plus x. So take the derivative is 2x plus 1, multiply that by x. So I got 2x squared plus x, evaluate at 0, so I add nothing to it. And then I take this, and this turns into a column vector, 2, 1, 0. I multiply it times the inverse of what I form from here, right? Okay, that's going to give me out a column vector. Again, that's a column vector representation, which is A3. So now my transformation is just this, this, and this in that order. Okay, so that is my my transformation matrix. All right. So note that if A times VG is WQ, right? So I'm going to multiply this out. I'm going to get a vector in Q, right? That's what happens when, let's see if we go back a couple examples. Okay, so right, I had A times my vector representation gave me a vector out in Q, and that vector I got was T of V in terms of Q, right? So T of V is the same as W, right? Because W is a vector in W. So, right, so here I'm going to get out a vector in terms of Q. And if V and W are an isomorphism, meaning that the transformation given by A is onto and one-to-one, then there should be an inverse matrix that takes me from Q back into G. All right, so that's really just the reverse of this. I multiply by A inverse on both sides to get this. So as long as I'm an isomorphism, right, onto and one-to-one, that means that this transformation matrix is square, determinant is non-zero. That's from that big theorem that we had a long time ago that we have not added to because we're past all the basics at this point, right? A inverse is basically the transformation matrix for T inverse. So that's the transformation matrix with respect to Q and G is going from Q into the basis G, right? So our examples here, it's really just a repeat of what I did here. But we're just going the other way. Okay. Oops. So suppose that T is a transformation from P1 to P1. It's given by this 2 by 2 matrix. Remember, the dimension of P1 is 2 because you have x plus a constant, right? It's first degree polynomials. So it has 2 elements. These are 2 by 2 matrices. Or, I'm sorry, the transformation should be a 2 by 2 matrix. So this first P1 is given by the basis G, which is 2x plus 1, 3x minus 1 for our domain. Our codomain is given by Q. It's 1 and x plus 3. Okay, so we want to find the inverse of A to find this inverse transformation. So we want to take something that's in Q representation already in W and say, what did we have in here that sent us to this place? Okay, so for A inverse, we can calculate that inverse pretty easily, right? You swap the main diagonal, change the signs on the secondary diagonal, and divide, or I guess multiply everything by the reciprocal of the determinant. Determinant here is 6 minus 7, so negative 1. So 1 over negative 1 is just negative 1. We do all our special jam here. So this is my inverse matrix. Okay, so if I want to find the representation of this vector in terms of G, I have to go from where I am already back into G. So this is something that's already in Q. In fact, actually, this is just W. So I need to represent it first in Q, then transform it, and then send it back, right? So right now, this is not represented in Q. So I need to turn it into Q, transform it, And then I don't have to find the original v because it's not asking me for that. So that resulting coordinate vector I get should be fine. Okay, so first I need to set this up. Something times 1 plus something times the second basis vector will give me x plus 2. That's an easy transformation, right? So just in case, like, oh, again, how do we set this up? It's coming from here, right? This would be 0, 1. This would be 1, 3, right? Or you can think of it as nothing plus bx will equal 1x, right? And then a plus 3b equals 2. So that's how this comes. We take the inverse to solve for our stuff, right? We've seen this before. But this is a coordinate vector, right? So it's the representation of w in terms of q. That's what we were trying to do here. Okay, so I'm just reiterating that that's what we found. So, right, this is the setup. Note that if I want to get back to my original w, I would just kind of undo what I did, right? So obviously 1 minus x plus 3 will give me x plus 2, right? Sorry, other way around. So negative 1 plus x plus 3 will get you x plus 2, right? To turn this into v of g, I take my inverse transformation matrix and I multiply it times my w represented in terms of q. So that inverse matrix we found times this wq will get me 11, negative 3. And that's my vector representation of v in terms of the basis g. Now, if I want to find my original v, remember, these are the coefficients. Multiplied times the basis will, as a linear combination, will give me the original v out. So if I wanted to just figure out what that v was, I would take the 11 and negative 3 and multiply it times the basis vectors of g in order to get out that original v. Okay, hope this was helpful. Again, notice it's really just a repeat of the two same examples from the beginning of the lecture, repeated over and over again. You just got to make sure you're doing everything in the correct order, right? So really, this is a really important diagram here. As long as you understand what you have and what you need to get to, and that you're following these steps, right? In my coordinate vector, in my standard representation, in my basis, in my do I need to do a transformation? Is a transformation given, and I need to find the matrix representation of that? Like, what's going on? This is a very, very important diagram, along with examples 1 and 2. Right? These two examples, along with that diagram, should get you through this entire section of 9.3. Okay, so we're going to move into 9.4 in the next video. If you have not reviewed chapter 4.4, I highly suggest you do that for 9.4, and I'll say that at the beginning of 9.4 as well. But this video and 4.4 put together is really what 9.4 is about. So make sure that you're very comfortable on this material and on the change of basis material from 4.4 going into 9.4, and that will make sure you're ready for the content there.